here. It's a real pleasure to have Irene Shivaei here. I met her when she was still a graduate student at Ionizing in 2015. And her background is she went undergrad at University of Tehran, and then she started her graduate career at University of Riverside with Naveen Reddy, and in collaboration with the MOSDEF team at which is mostly deceased. Correctly. Yeah, and since then she's graduated and continued on to great things. She's now a Hubble Fellow at the University of Arizona. She, as you could probably tell, works mostly on high redshift, which is particularly relevant to certainly me and Lucy and our research teams. So it's great to have Irene here, and looking forward to your talk.
Thanks. Hi everyone. Well, thanks for having me here. It's a pleasure to talk about my science with you, and thanks for the nice introduction. So I want to start with this picture of our universe that started 13.7 billion years ago. About maybe 0.1 billion years after that, first galaxies started to form, and a little bit after, less than a billion years after, the universe changed its phase from completely neutral to an ionized phase in the intergalactic medium. That's called the Reionization Era, somewhere around here. And after that, galaxies form, they grow until the universe gets to the peak formation, the peak of star formation activity about 3 billion years after Big Bang. Some people call it cosmic noon. It's around redshift of 2. And after that, the growth of star formation rate density of the universe falls down until we get to present day 13.7 billion years after the Big Bang. So in this plot, I'm showing the history of cosmic star formation. This is the famous Maddow plot. Y-axis is showing cosmic star formation rate density. On x-axis, you see the redshift. So as I mentioned, our universe starts, the star formation rate density starts to grow. We reach to this peak, somewhere around redshift of 2, and then it falls back down until the present day. This evolution is thought to be determined by the growth of dark matter halos, which depends on the cosmology, as well as the distribution of star formation rate in these halos as a function of the halo mass and redshift. But in order to understand this full evolution and to better understand the formation of galaxies, we need observations over a range of redshifts, over the whole history of cosmic evolution. Local studies, surveys such as Sloan, provide us with a great endpoint of this story of cosmic evolution. They have large photometric and spectroscopic data sets for more than 10 to 6 galaxies that gives us detailed information about the properties of galaxies in the present day. But to fully understand the history of the universe, we need to go back in time and look at earlier frontiers. There are other surveys, here I'm naming a few spectroscopic large surveys that go up to redshift of 1. These surveys have galaxies about like 10 to 4, up to 10 to 4 galaxies, very large spectroscopic survey that gives us details about the properties of the galaxies up to redshift of 1. Now, if we move to higher redshifts, redshifts about 4 or 5, getting closer to the reionization era, there aren't really statistically large spectroscopic surveys. So this highlights the importance of looking at galaxies, studying the universe during this peak epoch of star formation activity. This is a very important era, well, because it's capturing the peak epoch of both the star formation and black hole activity in the universe. And it's the next step of understanding the evolution of the universe, going back in time. And any result from this studying galaxies in this era, we can use to extrapolate to better understand higher redshifts, getting closer to the reionization, important epochs of early universe. But how can we, so there are many still outstanding questions about galaxies in this era. How can we tackle these questions? a significant part of our knowledge from galaxies is coming from the radiation from massive stars. And remember that at redshift of about 2, the cosmic noon, our galaxies are very star-forming. So the light that we get from galaxies is actually dominated by the integrated light that we get is dominated by the light emitted from the most massive star and the ionized gas around them, as well as the reprocessed UV and optical light that is coming from the dust particles in longer infrared wavelengths. So one of the main questions, and one main question that I want to address in this talk is, what are the characteristics of these massive star populations during the peak epoch of the star formation activity in the universe? These galaxies are very star-forming, and I said that the light is dominated by the light from the massive stars. So we need to understand the characteristics of massive stars in order to better understand the galaxy formation and evolution at this epoch. And in order to do that, we need to look at galaxies over a large range of wavelengths. This is a spectral energy distribution of a typical star-forming galaxy, flux versus wavelength. The light, shorter wavelength light is coming is showing the stellar part of the galaxy. So the UV is dominated by the light from the most massive stars. As we go to longer wavelengths near infrared, this is coming mostly from an older population of the stars. And the stellar light, UV and optical, get absorbed by dust particles inside the galaxies and re-emitted at longer infrared wavelengths. So here, the mid-infrared part of the spectrum is the UV light that is absorbed by small dust grains, heated to high temperatures, and re-emitted at certain wavelength in the mid-infrared. And the far infrared wavelength is coming from light absorbed by larger dust grains that are in thermal equilibrium with their surrounding. At lower temperatures, they emit light in far infrared. So in order to really capture a complete picture of a galaxy, we need a coverage, full coverage over full electromagnetic coverage over range of wavelength from the galaxy. And just to emphasize the point of these multi-wavelength observations, here I'm showing the same Maddow plot, cosmic star formation rate density versus redshift, but this time the plot is divided into 2 components of unobscured and obscured star formation. And as you can see, at certain redshifts, especially the ones that we are mostly interested in, the obscured star formation rate can be as large as 10 times the unobscured part. So this is just highlighting the importance of taking into account both components of the star formation activity in galaxies when you're observing them. So if we get this full coverage from UV to IR, we can cover the stellar and dust emission from galaxies. But what if we want to also learn about the ionized gas and the H2 region in the galaxies? We need deep rest frame optical spectroscopy. Rest frame optical spectra is the emission lines in the rest frame optical spectra is coming from the ionized gas, the H2 regions around massive stars. And here I'm highlighting the main nebular lines, the main nebular emission lines. These lines are heavily studied in the local universe. These diagnostic lines are well calibrated and tested in the local universe to give us information about the physics of the ionized gas. So at high redshift, we can use these to better understand the H2 regions. Now, let's briefly take a look at what we actually learn about this, using these emission lines, what can we actually get out of them. The Balmer lines, H alpha, H beta, gives us our indicators of star formation rate. These lines are coming from the H2 regions around the most massive stars. So they have very short time scales. That's why they're almost an instantaneous star formation rate indicator. The ratio of the 2 lines gives us an estimate for the nebular dust attenuation. We know the theoretical value of the ratio of H alpha to H beta. And given that these are separated in wavelength, any deviation from that theoretical value gives us information about how much dust we have in the nebular region. If we add more lines, we can estimate the gas phase metallicity. Also, O2, combining O2 with these lines is another indicator of the gas phase metallicity in the galaxies. And the ratio of the two different ionization states of the same species, O3 to O2, gives us an estimate of the ionization parameter in the ionized gas of the galaxy. And looking at the ratio of the doublets of the same species, for example, the doublets, the two lines of S2 or O2, we can constrain electron density because it's sensitive to the number of to the density of electrons that are available for collisional excitation and de-excitation. And hence we can get an estimate of the electron density using those ratios. And combining multiple lines, we can also understand about the AGN activity in our galaxies. So as you can see, with just a few number of lines, or 6 lines highlighted here, we can learn a lot about the physics of the ionized gas in the galaxies. And luckily, at high redshift, at redshift 1.5 to 3.5, all these lines are shifted to the near-infrared atmospheric windows that are available to us for ground-based spectroscopy. Here I'm highlighting redshift 1.5, 2.3, and 3.4. Maybe the best redshift window is 2 to 2.6, where O2 is in J-band, H-beta O3 are in H-band, and we have H-alpha, N2, and S2 in K-band covered. So we can cover all the main optical emission lines in near-infrared wavelengths. However, keep in mind that getting these emission lines, we need deep spectroscopy. It requires long integration times. And in the past, the near-infrared spectrometers that we had on ground-based telescopes were single-slit spectrometers, so we were able only to observe single objects at a time. So really, there wasn't an efficient way to get large samples of redshift 2 galaxies with covering all the optical emission lines in multiple filters. And with the advent of multi-object near-infrared spectrometers, such as MOSFIRE on Cake, FMOS on Subaru, KMOS on BLT around maybe 10 years ago or so, less than 10 years ago, now we are able to efficiently get large samples of redshift 2 galaxies with deep frame optical spectroscopy. So for example, MOSFIRE on Cake is able, in a single mask, is able to get spectra for about 30 objects at one time. So this becomes the motivation for the MOSDEF survey. MOSDEF stands for the MOSFIRE Deep Evolution Field. It's a large spectroscopic survey that uses MOSFIRE on Cake to get rest frame optical spectra for galaxies at redshift 1.5 to 3.8. So capturing this peak epoch of star formation activity in the universe. MOSDEF is a large collaboration between 4 UC campuses. On the left, you see a picture of our team meeting at UC Riverside 2015. All the 6 co-PIs are in the picture, and they're graduate students. But the funny thing is that all of us, the graduate students, are now graduated, have moved on to new institutions. There are new graduate students working, but I don't think we have an updated picture with the larger team. The observations were from 2012 to 2016, 4-year, about 50 nights. And at the end, we got a catalog of rest frame optical spectra for 1,500 galaxies, all H-band selected, a complete sample done to stellar mass of about 10 to 9 solar masses. And the redshift ranges were selected so that we can cover all the main optical emission lines in the near-infrared bands. And here you can see an example of a 2D spectra and the 1D extraction of the galaxy at redshift 2. Another important thing about the MOSDEF survey was that these galaxies are all located in the famous extragalactic fields, the Candle fields, which means that in addition to the near-infrared spectroscopy, we have access to a wealth of ancillary data from space-based telescopes covering the full wavelength range from UV to far infrared. And in this talk, I'm going to use data from all these telescopes to tackle the question of what are the characteristics of massive star populations at redshift 2 by looking at their stellar continuum emission, the emission from ionized gas, and emission from dust. So in this very simple picture, I'm showing the emission from a massive star. The main emission from a massive star has two components: a non-ionizing UV component, which is mainly which is coming from the stellar continuum from massive O and B type stars, and it has another ionizing component that ionizes gas around it, make the H2 region, producing nebular recombination lines such as H alpha and H beta that are mainly coming from more massive, the most massive early O-type stars. Now going back to this picture, we talked about how much we can learn by from using the optical emission lines. Now, what else can we learn if we add more information? If we add the UV photometry, which is covering this stellar continuum, we can learn about the fraction of the massive O stars compared to slightly less massive later type O and B type stars. And to show this point, I'm here showing a simulation of a burst of 80 solar masses per year on top of a constant star formation rate, luminosity versus time. This is where the burst of star formation ends. Red is following H alpha luminosity and blue is following the UV luminosity. And as you can see, after the end of the burst, H alpha reacts to the end of the burst very quickly because it's coming from these most massive stars, while it takes a longer time for UV to act because there are longer-lived stars that are still in the population emitting UV light. So by looking at the ratio of H alpha to UV, we can learn about these most massive stars. And the quantity to do that, a quantity that can be useful for this ratio of H alpha to UV is ionizing photon production efficiency, or psi-ion. Ionizing photon production efficiency is basically the ratio of production rate of hydrogen ionizing photons to the ratio of UV continuum luminosity, which is proportional to H alpha to UV luminosity. Why do we care about psi-ion? Why psi-ion is important? First of all, because it tells us about the massive stars population. It tells us about the relative number of massive ionizing stars to non-ionizing stars, which is affected by the initial mass function, the star formation, recent star formation rate history, and age of the population. It also tells us about the ionizing photon production rate of those massive stars, which is affected by the stellar metallicity, the binarity, and rotation. So basically the properties of these massive stars. But also, psi-ion is an important input in the cosmic reionization models. It's one of the three parameters that determines the ionizing emissivity of galaxies. And tells us, so by constraining this, in addition with these two other parameters, the escape fraction of ionizing photons and UV luminosity density, we can learn whether galaxies were, at reionization era, whether galaxies were able to produce enough ionizing photons to reionize the universe or not. So with MOSDEF, we have a large sample, about 650 galaxies, with UV coverage, H alpha and H beta coverage, which can give us dust-corrected, robustly dust-corrected H alpha luminosity and UV luminosity to determine psi-ion at redshift of about 2. So here I'm showing one of the plots, one of the results from this work. On the y-axis, we have psi-ion, the ionizing photon production efficiency. On x-axis, I'm showing the ratio of N2 to H alpha, which is using the empirical calibrations from local studies, converted to gas phase metallicity. So metallicity is increasing in this direction. As expected, psi-ion and gas phase metallicity, they are anti-correlated. As we get to higher metallicities, we have lower fraction of ionizing photons. The first explanation is because if we assume gas metallicity is following stellar metallicity, as we get to higher metallicities, we have less, we have more line blanketing and hence less fraction of ionizing photons coming out. So the yellow points are showing the composite spectra, and which is kind of the average of the individual measurements. An important implication of this anti-correlation between psi ion and metallicity is what we see about psi ion in the famous diagnostic BPT diagram. So BPT is named after its creators. It's a diagnostic diagram that uses a set of nebular emission lines. Here is O3 over H beta, N2 over H alpha, to distinguish the ionization mechanism of nebular gas from whether the gas is ionized by the UV photon from stars in star-forming galaxies, or is ionized by harder radiation coming from the AGN. So these data points here are from a local survey, SDSS, a Sloan survey. The large data set of Sloan made it possible to clearly determine the locus of star-forming galaxies, as well as the line that separates the star-forming galaxies from AGN. But in addition to this empirical diagnostics, this diagram has been studied extensively with stellar population and photoionization models as well to determine this separation line as well as the locus of star-forming galaxies and AGN. Now, if we only focus on the star-forming part of the diagram and compare it with what we see at redshift 2, there is a shift of there is a shift in the locus of star-forming galaxies at redshift 2.3 compared to redshift 0. So these are massive galaxies strictly chosen to have well detection in all these lines at the redshift of 2.3. And as you can see, the white is the running median of redshift 0 galaxies compared to running median of redshift 2.3 galaxies. There is a shift towards higher O3 over H beta and higher N2 over H alpha. Now I'm going to remove the underlying local galaxies and just look at what we have at redshift of 2. So here the axes are the same, O3 over H beta versus N2 over H alpha. The solid line is showing the locus of a star-forming galaxy at redshift 0. And the dashed line is the shifted curve of redshift 0 curve to higher values in the y and x direction so that it fits our redshift 2 galaxies. As you can see, the shift is towards this direction, and there are many explanations of why we see this shift. One major proposed explanation is that galaxies at redshift 2 have harder ionizing radiation, which is causing this offset. If that's the reason, we should be able to see an increase of psi ion value in that direction, because psi ion is directly tracing the hardness of ionizing radiation. But if I color code these data points with psi ion, we don't see any shift in the direction of the offset. The increase is actually in the perpendicular direction, which is basically an increase in direction of the metallicity. So lower metallicity galaxies have higher psi ion, which is the same thing that we saw in the first plot.
Sorry, can I ask you a question about this? So if you're using the lines to derive psi ion themselves, the line ratios at some level,
Yeah.
so that must go into this information, right? So you're saying that both.
You're saying there's degeneracy.
Yeah, right, exactly. Yeah.
Yeah. Yes, we are using the H alpha and H beta. There is some kind of dependence, but it's not in a very clear direction.
Okay.
But yes, yeah.
Yeah. I didn't know if it was more into the radio transfer modeling or something that's going into that direction, but not yet.
No, I mean the psi ion is. No, we're not using any modeling
Got
for
it.
that. It's
Okay.
just the H alpha luminosity to UV luminosity.
Got it.
And yes, the same line is, so it might be affected, but it's not a very obvious because both are in both directions,
Yep.
both axes. So the conclusion is So one result of this study was that there must be other explanations for this offset in the VPT diagram. For example, a larger abundance of nitrogen compared to oxygen at redshift 2, which is causing this duration or different electron density. But it seems like the larger N/O ratio is more favorable. Another important result is how psi ion changes as a function of UV continuum slope. Beta or UV continuum slope, especially at high redshift, is commonly used as a way to correct UV luminosity for dust attenuation because it mostly changes with the amount of dust as opposed to other parameters like the age of the galaxy. So higher values of beta means the galaxy is dustier compared to low beta. And here is our result. Again, the orange points are showing the result from the composite spectra, which is kind of following the average trend. At high values of UV slope, psi ion is almost constant, but as we get to blue beta values, psi ion increases to higher values. And this is in agreement with studies at higher redshifts, redshift 4 to 5, that again, we see a boost in the value of psi ion as we go to very blue beta galaxies. And why this result is important, because these galaxies with blue beta are similar to what we have at higher redshifts during the Reionization era. And as I mentioned before, constraining the value of psi ion for these galaxies tells us about the ionizing emissivity and whether the galaxies were able to reionize the universe or not. So now let me show you this gray horizontal line here is from Robertson et al. 2013, and it's the nominal value that is used for reionization models. We are finding that psi ion is elevated compared to this value, meaning that in order to get the enough ionizing emissivity, we would need lower escape fraction of ionizing photons for this galaxy. So I just want to highlight that although this study is for galaxies at redshift of 2, with carefully selecting the sample to those that are analogs of higher redshift, we can extrapolate these results to higher redshift, getting closer to the reionization era. Another important part of this study was to look at the large scatter that we see in the individual measurements. So if you look at the blue points and the triangles are all individual galaxies, and there is a large scatter. What is causing this scatter? Is it only uncertainties, different types of uncertainties, or is it actually telling us something about the underlying physics of massive stars? So here is the distribution of the whole sample, distribution of psi ion for the full sample. And when we subtract the measurement uncertainties from the observed scatter, we still end up with a large scatter of about 0.3 dix. One of the main uncertainties in these kind of calculations is how we are correcting our H alpha and UV luminosities for dust attenuation. At these redshifts, the most commonly used attenuation curve is the Calzetti curve. However, recent studies are suggesting that maybe a different, steeper attenuation curve, like SMC and SMC-like attenuation curve, is more applicable for high redshift galaxies. So to see how much this different choice of attenuation curve will affect our results, we repeated the calculation, this time using an SMC curve. And as you can see, there is a large shift of about 0.2 to 0.3 dix to higher values of psi ion if we use an SMC curve. The uncertainty, however, is not only systematic, there is also a random uncertainty associated to this kind of calculations because we are assuming a single attenuation curve for the whole population of galaxies, which is not realistic. It's probably more function of stellar mass or specific star formation rate in the galaxy. In order to figure out how much that is adding to our scatter, we did some simulations, and we calculated about 0.1 to 0.2 dix uncertainty that is added to the scatter.
So, I mean, you actually change the curve and the LSC. So if you only change the curve and not the LSC, what would the result?
The difference would be smaller. But the reason of this choice of lower metallicity is also because this is more typical for our higher redshift galaxies. So basically, I wanted to compare what we think the higher redshift galaxies are with SMC and the subsolar metallicity, and compare it with what we usually assume in higher redshift studies.
And if you use the concept of starburst curve on 2, presumably it would be more harm than yes.
It would be closer. Still,
I understand there's still
Yeah.
an offset, but then like, I think it would be consistent with your yellow dump out there. Right?
yeah, I don't remember the number, but I can go back and look how much.
So
that
it's,
changed.
I guess my point is it's not as realistic, at least from what you're showing here, I would argue.
Okay. Yeah.
Which makes sense because obviously the galaxies are all lower metallicity.
That's actually another. So another thing about this study is that we're this subsolar metallicity is probably a large fraction of our galaxies are above 10 to point, not a large, but a fraction of our galaxies are above massive 10 to 11, 10 to 10.5 solar masses, and we should probably use a combination of like high metallicity CAT-ZE, lower metallicity SMC.
No, I understand that, and then you just kind of open the Pandora's box,
Exactly.
but yeah, I just wanted to just clarify that it's really one of each of our metallicity.
Yeah, that's good.
Sorry, just a little bit, I mean, SMC is only defined for low metallicity. There is no high metallicity SMC law, right? I mean, when you're talking about changing the shape of the EP and the dust attenuation curve is one thing. But yeah, so it's not like they're, right, it's just measured empirically to be that, right?
Was there another question? By looking at these, the measurement uncertainty, the uncertainty we get from the variations in dust attenuation curve, we still end up with a large scatter, which means that this scatter is intrinsic and is telling us about the variations in the stellar population of these galaxies. So using stellar population synthesis models, we can predict the value of psi ion. Here, I'm showing the model predictions on this part of the diagram. This is the prediction from BPAS, which is one of the SBS synthesis spectral SPS models for a saltpeter like a typical saltpeter like IMF, a constant star formation history, and a subsolar metallicity. So this is what we get from this prediction. Now I'm going to tweak different parameters of this model to see how much variation we get in the value of psi ion. If we add a binary evolution, we get a higher value of psi ion, mainly because in a binary evolution system, the main sequence lifetime of the less massive less massive companion increases, the star becomes hotter, and it produces more ionizing photon. If we change the parameters, the high mass and parameters of the initial mass function, the slope or the high mass cutoff, we get a range of values for psi ion because we are basically changing the ratio of massive stars to less massive stars. If we change the stellar metallicity, obviously again we get a different value of psi ion because we are changing the amount of metal blanket. Now this is just showing that if we use a different stellar population synthesis model, the Broussard-Charlot 2003, we get a slightly different value from our fiducial BPAS, but still they are consistent. And if we change the star formation history, instead of a constant star formation history, if we add a burst of 5 or 10 times of star formation on top of our constant star formation, we get, again, a range of values of psi ion. So the conclusion is that by looking at psi ion, we can learn a lot about not only the ionized gas through the BPT diagram, but we can also understand galaxy-to-galaxy variations in the initial mass function, stellar metallicity, binarity, and star formation history of our galaxies. Now moving to the next part, we talked about the ionizing and non-ionizing radiation that is coming from our massive stars. But these photons will be absorbed by dust particles and re-emitted at longer wavelengths. Going back to this simple cartoon, if we want to make it a little bit more realistic, we should add dust to this. So the UV photons will be absorbed by dust particles around the massive stars, and they will be re-emitted at longer wavelength. One of the important components of dust in the ISM of galaxies are PAHs. These PAHs are organic molecules. They are aromatic. They have aromatic features. They are in rings of carbon with the edges of hydrogen atoms in the surrounding. These molecules get absorb single UV photons, get transiently heated to very high temperatures, and re-emit mid-infrared photons at certain wavelengths. The most prominent one is the emission at 7.7 micron, which the combination of these emissions, these aromatic emissions, can account for up to about 20% of the IR emission of galaxies. Fortunately, at redshift of 2, the emission from PAH molecules can be traced by, Switzer MIPS 24 micron instrument. And given the relatively high sensitivity of MIPS 24 micron, we are able to individually detect redshift 2 galaxies, individually detect the mid-infrared emission of redshift 2 galaxies, while other infrared instruments such as Herschel, we have to rely on combining the images, stacking the images to get detection. So Spitzer MIPS 24 micron gives us this amazing opportunity to trace the infrared emission of individual galaxies at redshift 2. So back to this plot, we learned that by combining the emission from ionized gas with the stellar continuum, we can learn about all this stuff. Now, if we add the infrared, mid-infrared emission, we can also learn about the obscure star formation and the properties of the PAH molecules in galaxies. Now, in the local universe, we know that the pH intensity scales with metallicity. As we go to higher metallicities, we have a higher intensity of pH. Naively, you may think that, okay, pHs, these are carbon-based molecules, so it should scale with metallicity. As we go to lower metallicities, there is a drop in the intensity. But this kind of correlations has never been studied at high redshift, mainly because due to lack of large samples that have metallicity measurements and at the same time pH measurements. But with MOSDEF, we have this opportunity of looking at this correlation because we have nebular lines to calculate the metallicity, and using the Spitzer MIPS 24 micron data, we can estimate the pH intensity. So in this plot, pH intensity is on y-axis, metallicity is on x-axis from the MOSDEF data, and following in agreement with what we see in the local universe, there is a correlation between 7.7 micron luminosity and the gas phase metallicity for a given star formation rate. However, this drop is happening at slightly higher metallicities compared to local universe, and there are multiple explanations for why is this real, or is it just a miscalibration of metallicity at high redshifts. But why do we see this correlation between pH intensity and metallicity? In order to address the explanation of this correlation, we looked at pH intensity as a function of other parameters. So on top right, I'm showing ionization parameter, which is coming from the ratio of O3 to O2 emission line. These are emission from different ionization states of the same species, and empirically we can convert it to the ionization parameter. And here I'm showing pH intensity as a function of age of the galaxy. So there can be two explanations. Before going there, here we see that pH intensity anti-correlates with the ionization parameter, so that at environments that have higher ionization parameter, harder ionizing radiation, more intense ionizing radiation, we see a lack of pH intensity. And at younger ages, again, we see that pH intensity drops. So the trend is seen in both of these diagnostic plots as well. So there could be two explanations. First, the nurture scenario is that there are just not, the pHs are destroyed more efficiently in environments that have harder radiation, which also traces environments that have lower metallicities. Or the nature scenario that there are just not, pHs are not produced in sufficient quantities in galaxies with young ages. Because it's assumed that pHs are produced in the outflows of AGB stars after their death, and that has a time scale of about 400 million years, which is exactly where we start seeing the drop in the pH intensity. So in reality, the reasoning behind the correlation between the pH intensity and metallicity is probably a combination of these two. But regardless of the reason, because of the mass-metallicity relation, which is basically telling that more massive galaxies have more metals or more metal-rich, we see the same trend of pH intensity with the stellar mass of the galaxy. So here I'm showing the pH luminosity divided by the total IR luminosity as a function of the stellar mass. And this has important practical terms for the high redshift studies, because if you remember, MIPS 24 micron is the only infrared instrument that you can get individual detections for redshift 2 galaxies. And so it's commonly used, the emission at this wavelength is commonly used to infer the total infrared luminosity and to obscure the star formation in redshift 2 galaxies. So we need to well understand this conversion of pH luminosity to total IR luminosity to accurately trace and estimate the obscure star formation. On the left plot, the horizontal lines are showing the conversions from the literature that convert the pH luminosity to total IR luminosity. And as you can see, these conversions are only valid for the most massive metal-rich galaxies. And as we go to masses below 10 to 10 solar masses, these calibrations underestimate the IR luminosity and IR star formation rate by about a factor of 2. So an important implication of this result for high redshift studies is how it affects the slope of the star formation rate stellar mass relation. So SFR stellar mass relation is one of the important plots that study its evolution is a study that high redshift is commonly called the star forming main sequence of galaxies. But its slope is related to star formation efficiency of galaxies. So it's common to assume that the slope of this relation is around unity. However, the way we measure the star formation rate on the y-axis can affect the slope that we get for this relation. So here I'm showing calculations for the star formation rate from calibrations in the literature, where the unobscured star formation rate, UV, is added to the obscured star formation rate, infrared, where the obscured IR star formation rate is coming from converted to 24 micron using these conversions in the literature. Now, if you look at SFR and MSR relation, but this time calculating a star formation rate with H alpha and H beta emission, we see that the slope is a bit shallower, mainly because the star formation rate is higher at lower masses. So this is completely independent way of measuring the star formation rate, independent from IR and UV emission. And surprisingly, if you use
at this redshift though, how well are you sampling lower star formation rates? Because to some extent, your change in slope is really, I would argue, driven by your low masses. And so we know that the 24 micron and IRR are not, they have floor in terms of being able to measure star formation rate. And so how do you account for that for the lower masses?
they are, sorry.
There's a floor in the star formation rate detection.
So, yeah, these are stacks of 24 micron. So I'm not using, that's why we can do it on like down to these low masses. Is that the?
Sure. No, I understand that they're stacks, but I would want to start there.
Yeah. In order, like for the completeness, this is up to like maybe down to 10 to 9.5 solar masses. And down to there, we are complete with the massive sample. At the same galaxies that are going into this analysis are going into things as well.
Okay.
Now, if we, instead of these, these conversions are using a single value over the whole mass range of the galaxies. If we use our conversions that are mass dependent, the conversions of 7.7 micron luminosity to IR luminosity that are mass dependent or metallicity dependent, we get a very good agreement with independently derived H-alpha star formation rates. And hence a shallower slope of 0.7 compared to the unity slope that is assumed and calculated with these other measurements. And however, so this is this shallow slope, we think that cannot hold down to very low masses because it will cause the stellar mass function to diverge at low masses, basically because we are saying that there are too many low mass galaxies. So in order to really understand the slope of the SFR M-star relation, we need to probe galaxies to even lower masses and constrain the slope at lower masses. Another implication of this study is how this affects the IR luminosity density at redshift 2. To test that, we simulated galaxies that were drawn from the IR infrared luminosity function of McNally 2011. And we increased the IR luminosity of the low luminosity galaxies based on the results of this study, and recalculated the IR luminosity density, and we saw a 30% increase in the IR luminosity density at redshift 2, which also leads to an increase in the star formation rate density at redshift 2, because if you remember, the star formation rate density is a combination of, it has two components of infrared and UV, and we are basically saying that this part is increasing. And it also implies that we are reinstating the discrepancy between the measured stellar mass density and the integral of star formation rate density at these redshifts. So basically, this is the stellar mass density versus redshift. The data points are measured stellar mass densities, and the solid line is simply the integral of the star formation rate density, and you would expect these to agree with each other. However, we are now saying that this value is increasing, so reinstating the discrepancy. So I showed all these results using MIPS 24 micron data and Keck mass fire spectroscopic data. In the era of JWST, we will be able to build on these results extensively because of much higher sensitivity of the instruments on JWST. So Miri has not only a higher sensitivity, it has a smaller, has a higher angular spatial resolution, meaning that we will be able to observe redshift 2 galaxies without the confusion of the nearby objects. So it will be amazing. Here I'm just showing an estimate of the JWST Miri GTO program sensitivity that we will be able to go to lower masses, lower metallicity galaxies. Just a brief overview. As part, I'm at Stewart, University of Arizona. I'm part of the Miri GTO program. The part that I will be mostly working on with the PI, George Rickey, is having a multiband imaging survey with Miri. So in addition to higher sensitivity, better angular resolution, Miri also has multiple bands, meaning that we can now trace the PAH, multiple components of PAH emission at the same time, as opposed to having only a single 24 micron band that Spitzer provided us to only look at one of the components. So here on the right, I'm showing the footprints of the Miri GTO that is on top of the NIRCam GTO, the deep NIRCam and NIRSpec GTO is here. These are in good south. So one of the goals is to look at the different components of PAH emission at redshift 1 and redshift 2. These are the full width half max of the Miri filters. And as you can see, we can trace, it's basically like a very low resolution spectrometer, and we can look at the ratio of different components of pH molecules. We will learn a lot about the characteristics of these molecules, their sizes, their ionization states, how they are affected in different environments, given different radiation sources, etc. And in addition to this extensive study with Miri, we will follow up our targets with NIRSpec, and as I showed you before, we will have a rich data set with NIRCam, and you can see that how much we will improve on this sensitivity of our current data if we use NIRSpec and NIRCam. So here is cake. This is where all the results that I showed you are from, and with NIRSpec, NIRCam, we will do much better, higher sensitivities, larger samples. And on the right, again, this is the large NIRCam and NIRSpec GTO program in the Good South. This is a collaboration between Europeans and the European Extragalactic GTO NIRSpec and the UA NIRSpec GTO, which is at the University of Arizona. So in summary, I showed you that how simultaneous coverage of multiple rest frame optical emission lines at redshift 2 is crucial for untangling key physical processes in galaxies. How by having multi-wavelength studies, we can get insight about the stellar and dust components of high redshift galaxies. And going back to the question that I started from, what are the characteristics of massive star populations at redshift of about 2? We learned that in the BPT diagram, without a change, since the ionizing photon production efficiency is not changing, the offset cannot be explained by the harder ionizing radiation. The elevated psi ion is has important implications for the reionization models. And by looking at the ratio of H alpha to UV, we learned about the properties of massive star populations in the galaxies. I showed that the pH intensity scales with metallicity, and as a star formation, IR star formation rate indicator, it should be treated with caution, and I showed you the implications of how it affects the total IR luminosity and star formation rate density at redshift 2. And with NIRCam, NIRSpec, and Miri instruments on board of JWST, we will be able to expand all these studies to higher redshifts and covering a larger dynamical range of galaxies, lower masses, lower metallicity. Before leaving you with the summary slide, I want to just advertise for the conference that we are going to have in March, first week of March, University of Arizona. The abstract deadline is passed, unfortunately, but if you're interested to learn about this part of the emission of galaxies, or talk about it with other people, if you haven't submitted an abstract, consider registering for the conference. So thank you.
Irene, for a very clear and informative talk. Questions? Other than me and Casey. Casey.
I'll go into the dust. So, I mean, it was really great. I'm always, I don't know what the right word is, not concerned or terrified, but the evolution in just dust itself, right? So we've got, you're saying, well, lower the metallicity, suddenly the pod intensity drops. We don't really know why that is. There's been some implications. But no one ever seems to worry about the thermally emitting dust population changing or not. And we're still drawing references based off, attenuation laws that we assume are, I don't know, at least redshift invariant. And we have dust composition of metallicity and redshift invariant, except for the pods. I don't know, have you looked at any of these relations? It's sort of an open-ended question, so we have.
No, it's a great question, and yes, it's a huge concern. We are looking at to see if we can see any change of the attenuation curve with mass or metallicity. Mass is easier because with metallicity we'll just shrink our sample more and more because we need detection of it. So with MOS, using H alpha over H beta, we can get the attenuation curve. It's because it's an independent dust measurement. And using the SEDs, we can get the attenuation curve. So it's an ongoing project to see if we can see any change with mass. But there should be, I think there should be a change, because even only by looking at the pH metallicity, we see that the dust composition is changing at a certain, below a certain metallicity. But the scatter is large in the data, and that's why I said using mass is better, because we can keep a larger sample. I don't have any definite answer.
Yeah, no, I don't
but
think,
yeah.
I don't know if I was looking for a definite answer. That'd probably be the outcome of your meeting here. Yeah, I'm looking for other time. I'm gonna talk to you later, I think. So I'm looking for other time for people to ask questions.
Questions from, other than Casey?
I have 2 minutes.
You have 2 minutes, but I just want to make sure, especially from the graduate students, it'd be great to hear. Yeah, but this is more something we present with an opportunity to just share with everybody, not just amongst the graduate students. Okay, so you have one question.
Okay, one more question. I'm gonna get back to the reionization part where you're talking about the lucidity and the ionization parameter, whatever you call it, the psi ion, which looked, I mean, you're showing this evidence nicely that it goes up as you go to lower beta values of the rate of flood.
Yes, yeah.
Okay. Do you, is there any weird selection effect that could also cause that? Because I'm imagining those must be the fainter, lower luminosity objects. So do you begin to have trouble detecting H alpha and H beta? Does that induce a selection effect that would push you in that direction? I want it to be true. I want what you showed to be true. But I'm just wondering if, you know, you're hitting the limit of what you can do with either MOS fire or some of these lower luminosity objects.
Yeah, and that ties into the question I had earlier.
Yeah, that's a good point. I haven't looked at, so that elevated psi ion happens in the bluest beta.
Yeah.
And I haven't looked at the mass distribution of them to see if they're preferentially at higher masses, we're missing the, so I'm sorry, the other way.
Right.
I'll bet you
Lower
lunch,
mass.
I'll bet you lunch that they're all under 10 to 9.5.
Under the 10 to 9.
Yeah.
She's already paying for lunch. It's okay.
Which is why I did that.
Well, yeah.
Yeah, yeah, I should, I haven't looked at that distribution separately to see like if it's biased towards some.
I'll bet John gets lunch also.
But yeah, even if that's the case, I think steel is important for reionization because we don't have 10 to 11, dominant 10 to 11 population at those redshifts.
Well, those are my next questions. Are there any indication in the lower redshift universe of that kind of population? Just struck me, has anybody actually looked at, you know, these really low beta things, these really blue things, and do they also show this prevalence for higher psi
Yes,
ions?
yeah, yeah.
Okay.
Yeah, these,
Sorry, they're very rare though. I mean, people have tried to search
In
for
the
them
local.
in the local universe.
Yeah.
I mean, there's the example by Photon, but that's all 0.3, and I don't even think
Yes.
that they have such high psi ions.
they don't, mostly at local universe, when they have those analogs, they're rare, but they look at the escape fraction,
Not the psi ion.
not the psi ion necessarily. But the O3 emitters, for example, they have high psi ion.
Sure.
And in that,
Sure, they're selected to be that way.
yeah,
That's
exactly.
what I'm wondering.
Yeah, they're selected. So that was my point on the other one too. Even if we are kind of biased for that sample, it's not necessarily because we think we want those low mass galaxies to say something about the higher redshift reionization era galaxies.
Right.
So even if it's biased, it's not necessarily affecting the reionization interpretation for reionization era. But in that plot, I also showed, that's not the local study, but Richard Bowen's et al. Study that has at higher redshift, they also have these blue beta galaxies with an elevated psi ion. But that's on a different data set, photometry data set.
Right, so
I'm just asking the
Slide
related
of
and
three.
last question, which is that is there any relation between psi ion and line alpha? Just because, I mean, I know it's a resonant line, but it just seems like with the O3 emitters, most of them do seem to have line and alpha. And if you're saying that psi ion sort of stringing these little things together, then that would imply that many of them would also have strong line and alpha. And that then I think could be interesting for the escape fractions, because that's directly related to that.
Yes, yes. I would expect to, there would be, but we don't have UV spectra for the galaxies.
Not yet, why not?
Not
You
yet.
have LRADs.
No, we are actually, there's,
Demos.
yeah, there's a, now we have.
Yeah.
We haven't used the data yet.
Yeah.
It's in the process of getting reduced, but
Some
so
graduate
far,
students in the corner.
well, it's mostly in the mean, but,
Oh.
yeah.